All right, hello. This is the continuation of our notes from today's class. We were looking at proportions and how to set those up with correct labeling. So we also had started CPI, but didn't get very far in it. So we'll go back to that section as well. But I wanted to backtrack first, starting with number 18 from the notes and start working through some of these. So we have Josiah went to Mexico for spring break and changed $325 into Mexican pesos. At that time, the exchange rate had $1 US as equal to 12.54 Mexican pesos. How many pesos did he get for his trip? So when you're doing these conversions with money, you're always going to have one fraction that represents your exchange rate, which is how do we convert the money between the two? So we have our US dollars and we have the pesos. And then we also have, what did Josiah have? Okay. So the exchange rate is that $1 US is 12.54 pesos. And Josiah came in with 325 US dollars. So we want to know how many pesos he's going to walk away with. So we'll cross multiply 325 times 12.54. 325 times 12.54 is 4,075.5 equal to 1 times x. So notice this is already solved. We don't need to divide since there's a 1 in front of our x. Now you probably won't get a part of a peso unless they tell you, decimal answers are okay. I would technically say you can't get a half a peso. So, I mean, I guess you could, but I don't really know what that currency would probably be something else. So for this purposes, they're not going to give you more money than what you had. So I would say they would probably round down here, even though the rounding up is the rule. They're not going to give you more money than you actually had to give for the exchange rate. So I would say he would approximately get 4,075 pesos. They won't, in the real world, round up if you didn't have that much money. Okay. So on Newton, just pay attention if they have rounding rules or not for those specific problems. All right, the next one, and actually next two, these have to do with ratios of calories in a specific measurement of a drink. So we have a 16-ounce iced caramel macchiato has 230 calories. How many calories would there be in a 24-ounce iced caramel macchiato? So the ratio of calories should grow as you have more ounces. So if we set this up as the 16-ounce over the calories that go with it, which is 230, then the 24-ounce would be over how many calories? So if I cross multiply, I'm going to get 16x. 24 times 230, I got 5,520. We can triple check that with my calculator here. And then we're going to divide that by 16. So 345 calories in that larger drink. More quantity of drink, more calories. Okay. So now we have another one. A new 12-ounce lemon ice drink is advertised for having only 160 calories. So 12 ounces for 160 calories. But Sally is only wanting to drink 100 calories. So maybe she's trying to diet and cut her calories for the day. So she only wants to have 100 calories. So how much of that drink should she have? So if we cross multiply here, that's 1,200 equals 160x. So 1,200 or 1,200, either way you want to say that, divided by 160 is 7.5. So she can only drink 7.5 ounces of that lemon ice drink. Okay, we got another one. Sue's paycheck is $1,040 for 40 hours of work. If she works 30 hours next week, what will her paycheck be? So we know for this week, dollars per hour, we're going to keep that as our ratio. That was 1,040 over 40. Next week, she's only going to work 30 hours, so we should expect a smaller paycheck. So 1,040 times the 30 is 31,200 equal to 40 times X. We do our other diagonal and then divide by the 40. We're going to get $780. So that's what she would make working 10 hours less. Ben needs to convert 500 US dollars to Japanese yen. 1 American dollar is worth 123.3 yen. How many yen will he have? Okay, same kind of situation here. We have our exchange rate we're going to put over here, and you can put it on the left or the right side. Just keep it together. Okay. And that's going to be dollars over yen. So I have $1 is 123.3 yen. On the other side, we have what Ben has, which he has an actual 500 US dollars, and we want to know how many yen he will get when he converts. So this is 500 times 123.3. If we use our cross products, 61,650 equals X times 1, which is just X. So he's going to walk away with 61,650 yen. And remember, that's if he's going to Japan. That's how that currency will be obviously what he would be buying things in. So CPI. So we did a little bit of this in class right before we left. So let's just remind ourselves what it means. Consumer price index is remember, cost of a basket of goods and services that we've used to track inflation over time. So we did this one together. We kind of walked through it. We had a car price in 1987, and we wanted to know if it kept up with inflation, what should that car cost in 2017? So we had our actual value in 1987, which was the car price, the CPI value, which remember, it's not the year you're using the price of those goods and services, equals how much would our car cost if inflation maintained this growth over the 2017. Sorry, I circled the wrong one. The 1987 was on the left side and the 2017 was on the right side. And when we cross multiplied and solved this, we rounded to the nearest whole because they asked us to for the dollar. We got 21,146. Now, obviously, we would have to know what car that person had originally bought and then track it over time to see what the comparable car would be, and if that actually was $21,146, or if it was more expensive or less expensive. That would tell you if it was keeping up with the inflation based on the CPI. So I did notice after I saved these notes and printed them, my table cut off early and did not have the information we needed for 2 of the years. We can reference this one back on the prior page. We did have the 2017, but for this one right here, I don't have 2015 on here. So we're going to change this to 2005. I wanted to just make sure we use some of the different numbers that are in the table. In Newton, the CPI tables are provided for the problem you need. So you'll have the values you need, but I had, I don't know, something just happened to my table and it chopped off the last column. And then the other one or maybe the last 2 columns, the other one that was missing was 2020. So, and I didn't have that on the previous page. So we're going to do 2000. So just changing those just so they work with the chart that I have up above. So if a hamburger costs 38 cents, which I would write that as 38 cents, because cents, remember, is the after the decimal part. In 1979, what would the equivalent price be for 2017? So I'm going to go back to the previous page where I had the 2017. So that's the CPI, 245.12. So we have, and remember, your years are just labels for your fractions. It's just telling you which fraction you have on each side. So 1979 is going to be on the left. 2017 is going to be on the right. We're going to put our actual value for each and what is the CPI value. Okay. One of these things we don't know. So we knew the actual cost of the hamburger in 1979. We also can look at this chart right here and see the CPI value of goods and services in 1979. On the previous page, I did have the CPI for 2017. It was 245.120. And remember, we wanted to know what would the equivalent cost of that hamburger be in 2017. So what does the hamburger now cost? So by cross multiply, 0.38 times 245.12, so 0.38 times 245.12, that's 93.1456 for the decimal, equal to 72.6x. I'll need to divide by the number that's next to x. So divide this by 72.6. And I get roughly 1.28 because we're going to round to the nearest cent. So $1.28 would be the estimated 2017 price of that hamburger, if it keeps up with the trend of inflation. We think it would cost $1.28. Okay. All right, if the price of an oil change is $45 in the year of 2005, what is the equivalent price in the year of 1985? So we've got our 2005. It doesn't matter which one you put on which side, just be consistent with the values you put underneath it to make sure they're from those specific years. So in 2005, the actual cost of the oil change was $45. And our CPI for that year was 195.3. That's how much the goods and services in that basket they've been tracking would cost. In 1985, we don't know what the price of the oil change was, so we're going to find that based on the inflation changes. And we're going to put that over the CPI value for 1985, which is 107.6. If we cross multiply, let's see what we get. 45 times 107.6 is the diagonal where I know both numbers. So that's 4,842 equals 195.3 times x. We'll divide by the 195.3. And that gives me, if we round to the nearest cent, that's going to be 24.79 because the 2 will not bump the 9 up. So $24.79 for the 1985 oil change, according to inflation trends for the CPI. Okay, what is the price of tuition in the year 2010 if the price was $1,865 for the year 1995? So I have 1995, 2010. I'm going to have a fraction for each year. 1865 was the actual value of the tuition in 1995. We don't know what that would be in 2010. I need to look up the CPI for both. So 1995 was 152.4. That was the value of the goods and services. 2010 is 218.1. Get our calculator handy. 1865 times 218.1. That comes out to 406,756.5. We have to set that equal to our other diagonal part, 152.4x. We'll need to divide the number on the left by the 152.4 to get our x by itself. And that gives me, we're rounding to the nearest dollar, so that's whole number. So cents is 2 decimal places for money and dollars are whole number. So we look at the ones place and we look at the digit right behind it. That's a 0. That's not going to bump it up. So it's 2,669. That would be the tuition in 2010. All right, we have just a couple more of these. Find an equivalent price of a calculator in 1985 if you paid $15.89 in 2000. Remember, I had to change that because my chart didn't have the right length to it. It was missing 2 things. So 2000 is 172.2 for the CPI. That goes in our bottom. The actual price of that calculator that year was $15.89. I want to know how much did a calculator cost in 1985. So I need the 1985 CPI value, which is 107.6. We're going to cross multiply. Always, I know usually we do this diagonal first, but if I'm going to work it out on my calculator to make life easier, I do the diagonal first that has both numbers. So 107.6 times 15.89, because the diagonal that has both numbers will be the one that you're going to then divide by the other diagonal's number. So 1709.764 equals 172.2x. We'll divide this by the 172.2. And that comes out to $9 and to the nearest cent. So let's look at 2 decimal places. There's a 2 there and an 8 behind it. So it's going to be $9.93 for that calculator in 1985. Okay. We're looking at number 27 now. The price of a Big Mac at McDonald's was 65 cents in 1973. What would be the price of a Big Mac in 2019 if inflation were the only factor impacting the price? So notice they say it that way just because they're wanting you to use CPI. The CPI tracks the inflation. Other things might impact prices, like with the wage changes, which I'm happy people are getting paid more, but that in turn has increased companies to increase their prices for their goods and services more than inflation normally has been in the past. So, there's other factors. They could have a sale going on, there's different things that could be impacting prices, but we're just looking at what if inflation was the only thing. So that means CPI. Okay. We're going to round to the nearest cent. So we have 1973 and 2019. And our chart, like in Newton, sometimes it will only give you the 2 values you need. Sometimes it'll give you a list of them that you can pick from. So the price of that Big Mac in 1973 was 65 cents. We want to know, what does it cost now based on inflation? The bag of goods and services was 44.4 in 1973. It had almost 6 times larger in the 2019 era. So we're going to multiply our diagonal that has 2 numbers first, the 0.65 times the 255.675. And that is 166,17705. Make sure I got that right. Yep. And that's going to be equal to 44.4x. That doesn't look like a 4, but it is. So we're going to divide by the 44.4. Oops. Hit the wrong button. And this is about 3.74 if we round to the nearest cent, which is 2 decimal places. So that Big Mac, based on inflation, should cost $3.74 in 2019. All right, last CPI question before we get into our other, 2 more CPI questions before we get into our last topic for the video. We're going to be looking at some scaling things. So if the average price of a house grew with inflation, the average price of a house in 1992 should have been $97,337. However, the actual average price for a house in 1992 was $144,500. Did the average price of a house grow faster or slower than inflation? So if it should have been this and it's higher, that means we saw the average price going faster than inflation. Because remember, should have been is what the CPI would have tracked for us based on the inflation. So since this one is definitely growing much faster price-wise, we would say we could throw out any that say slower. Average price grew slower. Those would not work. So let's read our A and B option. The average price of a house grew faster than inflation because the actual value is higher than expected. Or the average price of a house grew faster than inflation because the actual is lower than expected. So to grow faster, you have to have an actual value that is higher than that expected or predicted inflation price. If we had one that was lower, then we would say it grew slower and it was lower. Okay. All right, last CPI for real this time. So it says the minimum wage in 1985 was $3.35 and it was $5.15 in 2005. If the minimum wage had grown with inflation, what would have been the expected value in 2005? So notice they actually gave us both dollar amounts, but one of them is, this is the actual 2005 value. We want the predicted based on the inflation. So even though we know the actual value of what people were getting paid in 2005, we want to say, hey, if they had gotten truly the value of inflation for all the things that have gone up in price, what should their salary have been? So we're going to have 1985 and we're going to have $3.35 over the CPI for that year, which was 107.6. In 2005, even though I know what the actual price is, I want to know what it should have been based on inflation. So this is the increase we saw in the CPI to 195.3. We cross multiply this. What you'll see is that people are not getting paid. That is not keeping up with inflation of how much we pay for goods and services. So this is 654.255 equal to 107.6x. We'll divide by the 107.6, and I get about $6.08 because it does not have a number that would bump the 8 up, and we're going to the nearest cent. Now you think, well, that's how much difference is that? Okay, so that's $6.08 minus 5.15. That means we're getting, in that specific moment in time, people were being shorted 93 cents from their pay per hour based on how much change there was in inflation on the goods and services that they needed to purchase, like groceries and oil changes and all kinds of stuff like that. 93 cents doesn't seem like a lot, but say you work 50 weeks out of the year, so maybe you get 2 weeks of vacation time, and each of those weeks you work 40 hours. So 40 hours a week times this difference in price times 50 weeks in a year, you've been shorted $1,860 from your salary. And the sad thing is that this scenario was back in 2005. It has only got much worse. Even with the increases in pay, the inflation rates are very, very, very high. You should look into some of that from the pandemic time. Inflation kind of went out of control, especially as we were starting to come out of that. So just interesting stuff that you can kind of think about for everyday life with the CPI. It's really intriguing to kind of compare some of these things. So the last part of the notes for today that we were supposed to get done so that you can get your homework done this weekend, it was just looking at just different applications using those proportions, using our cross multiplication setups. So this one, I had some of these in the pre-video for the week, essentially too, the one that's your weekly video assignment. So some of this is not brand new if you've already watched some of those. But this one's called using the rates and proportions to compare. So essentially, we're going to kind of think of a unit rate. So it says the city of Tourist has 298 hotels with a population of 386,202. In Tourist, how many people, not counting visitors, so just this population, do they have per hotel? So people per hotel. Now, since you just have those two values, you could just say people divided by the number of hotels and round it to the nearest whole. But we want to show you how you can do it as a proportion. So you can set up the number of people you actually have, or total number of people we have in our population, divided by the number of hotels, since they said per hotel. And then we're going to say, well, how many people is that per one hotel? So if you're kind of just reducing this down, essentially dividing it, like I said, but by cross multiplying, we'll get that we're doing this number times 1 equal to this number times x. So we end up doing the division anyways. So it's just a different way of thinking about it. If you automatically knew that you just needed to divide total population by the hotels to get that percent, or that not percent, that whole number, then that's fine too. There's no right or wrong on which way to do that. But they just wanted us to see we could do it with a proportion. So 386,202 divided by 298, rounded to the nearest whole. Okay, so we have a 9 behind our decimal, so that's going to bump that up to a 6. So that would be 1,296 people in Tourist per hotel. Okay. All right, how else can we use those cross multiplication proportions? Well, we can use them to do a comparison. Now, I found an error on this one after I reread it. It does not read correctly, probably because everything started with San and it was trying to auto-populate some of the cities. So I need to change some of the wording here. So it says, this should have said if San Diego were proportional to San Francisco. It just got reversed right there. But that is very important because that determines how you set up the problem. So let me underline that statement because that's one of the most important parts that you need to set up correctly, okay? So it says, I know that San Diego is proportional to San Francisco in parks to population. Okay, so that tells me a couple things. I'm going to be doing parks on top of my fraction, population on the bottom, and I'm relating San Diego to San Francisco. So I'm going to have my San Francisco fraction and my San Diego fraction, and we're going to use the actual San Francisco value for parks, the actual San Francisco population, because we're relating San Diego to San Francisco. So we're going to use everything that we know is true about San Francisco. And then we are looking for how many people would San Diego have. So we're going to use, this is going to be our predicted value. Okay. We also actually know the number of parks in San Diego. So usually on the second fraction, the one you're relating to the other one, we know one piece and we're missing one, or we might know both pieces, but they've specifically asked for a predicted value of one of them. We want people in San Diego. So actual number of parks in San Francisco is 220, population 883,000. Actual number of parks in San Diego is 340. We want to know predicted, if this San Francisco ratio holds true for San Diego, what do we expect the population of San Diego to be? That doesn't mean it will actually be the population of San Diego. It's the predicted value based on this proportionality to San Francisco. So 883,000, I'm doing the diagonal with both numbers first, times 340 is 300,220,000 equal to 220x. So we're going to divide by 220. And we're supposed to round this to the nearest, I believe, whole number because we don't usually have part of a person. 1,364,636, because the 3 behind the decimal would not bump the 6 up. So we would have 1,364,636 people in San Diego based on the proportional relationship to San Francisco. I'm just writing extra unit information to make that make sense. Newton would expect you to type in the number. And you might want to be careful with Newton. Make sure you read the directions. I write commas in class because it's helpful to read the number that way. They don't always sometimes want commas written into the answers. You kind of have to play around with that to make sure whether or not they accept the commas. Or if it's in the directions, do not enter commas. Make sure you do not enter them in. Okay, so we just have one more chart to look at, and then we have a couple more examples. So there is a lot in here, but I wanted to make sure you have everything you need to get homework completed for this week. So this one's just kind of more of what we've been doing, but we're just making sure you understand how to convert millions, billions, and trillions to standard form, and how you can also go back and forth with those with proper scientific notation. So some problems will have values followed by the words million, billion, or trillion. You can set up your proportions to see if the words will cancel during your calculations. When you cross multiply, if the written units do not cancel, you will need to translate the value into standard form, use powers of 10, or write the value in scientific notation. So we just want to make sure we know how to do all three of those different forms. So if my word problem says 320 million, because I've already worked out these top two rows, that is 320 followed by 6 zeros. Okay. Now, if I write this number directly as they've given it to me, that would be 320 times 10 to the 6. That's not proper scientific notation. It's just writing it using a power of 10 by using the word million as 10 to the 6. We talked about that a little bit in class and in the one of the video parts. So this in proper scientific notation, we would need to move our decimal 2 places to the left. So that'd be 3.2. And then remember, when you move to the left in scientific form, you add to the exponent. So that'd be 2 places to the left. We add 2 to the exponent. We get 3.2 times 10 to the 8th. I could type that in on my calculator and hit enter, and it should go back and give me this 320 million. Okay, this one's a little tricky. 0.67 trillion. If you think about that, I'm actually going to write it in this form first. So 0.67 trillion is times 10 to the 12th. If I put that in proper scientific notation, I would need to move to the right one to get that single digit in front of the decimal. And then we would be subtracting 1 from our power. So this is a little easier sometimes for people to convert back to the real form, especially if this has a weird decimal in it. Essentially, we don't even have a full trillion. So trillions, remember, are in that fifth group away from this, because this is ones, thousands, millions, then we would have billions, and then we would have trillions. So if you think about that, we are actually in this 0.67 is in the billion range because it's not a full trillion. So this would actually be 670 billion. And I'll show you how that works with this. So that's needs 3 more zeros. So yeah, ones, thousands, millions, and billions. Why is it 670? Well, because if there was a 1 here, then this would be 1,670,000,000,000 if you read it. I can check this though. This is 6.7 times 10 to the 11th. That means I move my decimal 11 places to the right to put it in standard form. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this one would probably be one of the trickiest ones. 52.86 trillion. Well, the 52 is going to be in the trillion group. The 860, because you don't see the third digit there since it's a 0, is in the billion group. I have nothing in the million group, nothing in the thousand group, and nothing in the 1 group that they listed in our decimals. So we're assuming those are all zeros. In just scientific form, but not proper scientific notation, we could write that as 52.86 times 10 to the 12th. I need to move 1 place to the left to adjust that to proper scientific notation. So 1 place to the left, we add 1 to the power. So 10 to the 13th. All right, so where is this helpful? Well, I have a one I've already worked out that I'll kind of read to you, and then we're going to do a couple together. So it says state A averages 205,000 deaths per year with a population of 22 million, while state B averages 12,003 deaths per year with a population of 0.99 million. Now notice they gave me the number of deaths and the number of population in both states. How do I know what my X is going to be? I read this statement. State B is proportional to state A. That means I'm going to use everything I know about state A. And this is how I knew how to stack my fractions. They said deaths per population. So deaths on top, population on bottom. Then I'm asking, out of the 2 things I already know about state B, because I do have actual values for both of them, I want to predict the number of deaths that state B would have if it was the same proportion as state A's. So we're making them have an equivalent ratio. That may not be true in real life because we're going to see that cities don't behave the same. There's not always the same crime rates and things like that, or sicknesses or illnesses. But the goal of this is to make a prediction based on someone telling you that they are proportionate. Okay. So we have our 205,000 deaths from state A, and our population for state A, notice I just wrote as 22 million. I have 0.99 million for the population of state B, and I'm guesstimating or predicting the number of deaths in state B based on the ratio of state A. So I went ahead and wrote this out, and I wanted to show you what they were talking about when they said the words might cancel. So if we write this out with just the words million and we cross multiply, keeping the word million in both parts, notice you get 205,000 times 0.99 million over, because we're going to be dividing by this part, the one that's next to X, 22 million. Notice that the word million is on both top and bottom here, so it can cancel out. That is what they meant by your words might cancel, okay? So if the words cancel, we can mark them out and then just do the math. So 205,000 times 0.99 divided by 22 comes out to 9,225 deaths predicted in state B based on proportionality to state A, okay? Again, that's lower. So what that tells you, why is that important? I can tell from that state B has a lower death rate, or excuse me, has a higher death rate, than state A, because we predicted if state B and state A were easy peasy matchy, right? If they had the same proportion of death to population, we should only see 9,225 deaths in state B. We saw 12,000. in the real world. So that tells me, oh, state B may or may not be a safer place to live, depending on what are the people dying from. Are they dying from car accidents, crime, sickness? Do they just have an older population in state B? There's more going on than just saying one's better than the other. But we do see that just from the numbers, state A has a lower death to population ratio than state B truly does in the exact values. Okay. All right, we're going to do some more of these. So these are a lot of Starbucks ones. It says the 27 Starbucks in Atlanta with a population of 0.5 million. Brooklyn has 142 Starbucks with a population of 2.53 million. Notice I have the values for both, but I'm going to look at my statement. If Atlanta were proportional to Brooklyn, that means we're going to use all of Brooklyn's information. Okay, so 142 Starbucks. Population of 2.53 million. Okay. How many Starbucks should Atlanta have if it's proportionate to Brooklyn? So Atlanta, even though we know how many Starbucks they currently have, we're doing what would it be if it matched Brooklyn? And then it's 0.5 mil for its population. Okay, so let's cross multiply. So we have, do the number ones first. So 142 times 0.5 million, keeping the word there just for now. And then this is going to be my X part. So I'm going to end up dividing by the 2.53 million. Notice there's a million on top and bottom, so I can cancel the words out. So this is 142 times 0.5 equals 71 divided by the 2.53. So roughly 28 if we round to the nearest whole. That would be 28 Starbucks in Atlanta based on proportionality to Brooklyn. Now that's actually super similar to what Atlanta actually had. So that means that Atlanta actually had a little less. It had one less. So there's a little bit higher ratio of Starbucks to people in Brooklyn, but not much. It's pretty close to the actual value that we were given. All right, let's look at 33. It says there are 27 Starbucks in Atlanta with a population of 0.5 million. Brooklyn has 142 Starbucks with a population of 2.53 million. If Brooklyn were proportional, okay, so this time we're switching it. Brooklyn is proportional to Atlanta. So we're going to use all of the values from Atlanta, and we're going to predict or guesstimate based on that proportion in Atlanta, how many Starbucks should Brooklyn have. So Atlanta had 27 Starbucks over 0.5 million people. Brooklyn, we're going to guesstimate based on this ratio over here, or predict how many Starbucks should it have for its 2.53 million people. And after this one, I'm going to show you a different way. Instead of writing the word million, we're going to write the scientific notation, just so you can see that if you don't like seeing the words, you can do this numerically. So this is 27 times 2.53 million equals, and then it would be 0.5 million x. We're going to divide by 0.5 million. That'll give us x over here. Notice I have matching millions again on top and bottom, so that reduces out. So 27 times 2.53, and then divide by 0.5. That'd be 137 if we round to the nearest whole number. Now, that looks a little bit more off, and that's because we're trying to, they have such a larger number of Starbucks. Losing one Starbucks in Atlanta is very much different than how much they would lose in the Brooklyn because of the concentration of the Starbucks. They have a lot more there. And this would be Starbucks in Brooklyn based on proportionality to Atlanta. Again, I'm just writing extra information in there for you, just so you can see kind of that number and its relationship to what we would be actually solving for. Okay, so we have Chicago has 570 parks for a population of 2.706 million people. Phoenix has 1.66 million people. Phoenix is going to be proportional to Chicago. So I'm going to use everything I know about Chicago in people to parks. So we're going to put people on top Parks on bottom. How many parks would we expect in Phoenix? Okay, so we've got Chicago, got Phoenix. And this time, instead of using the word million, I'm going to show you that I could do it with scientific notation. That would be times 10 to the 6 for both of those, but this is something I did on the weekly video. When I'm putting scientific notation into a fraction where we might be cross multiplying, I don't use the X in my scientific notation. I just write times with parentheses. And the reason for that is a lot of times we use X as our variable when we're solving, and a time symbol that looks like an X can confuse us when we're doing our solving step, okay? So notice I'm just kind of writing those as times 10 to the 6, but instead of a times symbol, I'm using parentheses to represent times, okay? So we have people in Chicago was 2.706 times 10 to the 6 over parks, which was 570. Phoenix, we're looking for the number of parks, so that's going to be X. And the number of people was 1.66 times 10 to the 6. It's so easy to write the habit of the time symbol. So we're going to cross multiply here. I'm going to do the number one first. So that's 570 times 1.66 times 10 to the 6. And we're going to be dividing that by the one that's across from X. You kind of start seeing a pattern the more of these you do. Notice that when the million word canceled, we were really canceling out two 10 to the 6s that match. So it is the same thing. As long as they're the same word, it is like canceling the same power of 10. So 570 times 1.66, and then divide that by 2.706, and round to the nearest whole. So this is one that this is you have to be careful of. This is a 6. I'm going to write it out. 349.667. That should be plenty for this. We look at this spot, we look behind it. The 6 is going to bump this up, but it becomes a 10. So then we have to carry the 1. So it's 350 parks. And that would be in Phoenix based on proportionality to Chicago. Okay. All right, so last page. I know it was a long set of things. This one right here is what if you get mixed units that don't cancel. So in other words, notice this one has millions, but this one has billions. We do have 2 millions in the problem, but we have this oddball throwing things off with that billion. So in this scenario, I would use the scientific notation, or at least even if it's not exact scientific notation, I would use the times 10 powers. It's just going to be a little easier to check if something cancels or not when you have different units. And if you can't cancel them, you can multiply in your calculator using the powers of 10. So Chicago is home to 2.706 million people, and the city sees about 55 million visitors each year. China has a population of 1.393 billion, and we want to know if their visitors, so China's, were proportional to Chicago. So we're going to use everything we know about Chicago. How many visitors would China expect? Okay, so I'm going to have Chicago. I'm going to have China. And we're doing their proportionate in people in their population to the number of visitors. Okay, so 2.706 times 10 to the 6 for the million. Okay, that's the number of people in Chicago. They see 55 million visitors every year. So that's 55 times 10 to the 6, because the word million is the 10 to the 6. China is going to have population of 1.393 billion, which is 10 to the 9th, because it's another group of 3 beyond millions. And then we're going to have that over the X, the visitors. Okay, now I want you to notice before I cross multiply, I can cancel the 10 to the 6s that both, we ended up getting lucky and having a million in the top and bottom of that fraction. So that is allowed. You can cancel a top and bottom of a fraction if they're multiplying and they're exactly the same. So that's one thing we can do, but we still need to cross multiply. So this would be 55 times the 1.393. Notice the 10 to the 9th does not cancel out though. And then we're going to have that set equal to x. We're going to be dividing by the 2.706. Okay. But canceling out those 10 to the 6s before we cross multiplied, and that's only true if they're in the same fraction together. That helps us with less numbers when we multiply. So 55 times 1.393 times 10, use my exponent button to the 9th. That is a huge number, and then I'm going to divide that by 2.706. Now, they want us to write our final answer in scientific notation rounded to 2 decimal places. So I'm going to write out what I have, and then we're going to adjust it. So 28,313,030.08. And I know it keeps going, but that should be plenty. Now, to write this in scientific notation, here's my decimal. I need to move 1, 2, 3, 4, 5, 6, 7, 8, 9 places to get that to be 2.83, rounded to 2 decimal places after I've got the decimal in the right location. And then that was a movement of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So times 10 to the 10th. And that would be visitors in China. So that is 28 billion if we look at it in its standard form. So that's a lot. So the last one. Okay, so Oz is home to 1.7 million people and the city has 490 parks. China has a population of 1.393 billion. If the number of parks in China were proportional to the number in Chicago, not Chicago, that should say Oz. Sorry about that. Didn't cut it correctly when I was doing the rewording. So how many parks would you expect in China? Okay. So we're proportionate to Oz. So that means we're going to use everything we know about Oz, which is the parks over people. And we know that that is 490 parks and 1.7 times 10 to the 6. I'm using the 10 to the 6 because this is billions and this is millions. They're not going to cancel. I don't know the number of parks in China, but I do know that their population is 1.393 times 10 to the 9th. Okay, notice no 10 to the 6 that can cancel here. So we're going to have to just cross multiply with all of our numbers. So I usually do the diagonal that has all numbers first. So 490 times 1.393 times 10 to the 9th equals 1.7 10 to the 6th times x. We're going to divide all of this over. So 490 times 1.393 times 10 to the 9th divided by 1.7 times 10 to the 6th equals x. Now, you could do some subtraction of the exponents because you do have 10 to the 9th over 10 to the 6th, but then you have to remember where to put that, and that's tricky if you haven't had algebra in a while. So I would just type all this in. You will want to be careful. You can do the numerator without doing anything fancy. You just straight multiply. But when you go to do your denominator, there's a specific thing you need to do. So that's my numerator. Before I type in any numbers, I went ahead and hit my divide button. You need to put the entire denominator in a parentheses. We're just doing 1.7 times 10 to the 6th. But if you don't put the entire denominator in the parentheses, your calculator will only divide the top number by the 1.7, okay? And then it multiplies that answer by 10 to the 6th. It doesn't divide by it. So it's really important that you do that step correctly. I'm also rounding this to scientific notation, 2 decimal places. So let's write it out first. 401, 511, 76 continues forever. This is the wrong place for scientific notation. I need to move that 1, 2, 3, 4, 5 places. And then round to 2 decimal places. That'd be 4.02. And remember, when you're going from standard form to scientific, it's if the original number was bigger than 10, remember that's a positive exponent. I didn't remind you of that up here. this original number, it's not just that I moved it 10 places, it's the original number was larger than 10. So you're going to have a positive exponent. If the original number is ever smaller than 1, which this is not, then you would have a negative exponent. Okay. So 4.02 times 10 to the 5th. And that is the end of this video.